Hey everyone, my name is Viresh, and my presentation is on analyzing the feasibility of regenerative fuel cells for the implementation in atmospheric electric aircraft. So let's get started. Right now, global carbon emissions from aviation are skyrocketing. There's been a 4 to 5% growth every year since 2010, and aviation share of global CO2 emissions on the rise. In fact, the aircraft industry is set to consume 27% of the 1.5C carbon budget by 2050. What this all means is that a shift towards carbon neutral electric aircraft is vitally needed in the long term future. As you can see by this graph, electric aircraft are more sustainable in both terms of the CO2 emissions and non CO2 emissions. But the barrier to electric aircraft in the status quo is the problem of energy storage. Batteries are really heavy. The problem with that is that because an aircraft has to lift that mass, that really limits their practicality. Right now, aircraft use kerosene, which has a specific energy of 44 megajoules per kilogram. Meanwhile, lithium-ion batteries have a specific energy of just 0.25 megajoules per kilogram. This huge discrepancy really limits the practicality of batteries for aircraft. But this is where regenerative fuel cells, RFCs, come in. They combine electrolyzers and fuel cells together into one system. The benefit is that they have significantly higher specific energies as a result. The way it works is that we have a photovoltaic array, taking in sunlight and turning into electricity that can then power the aircraft as well as the electrolyzer. This electrolyzer takes in water and electricity to create hydrogen and oxygen gas. Then, during the nighttime, when there is no sunlight available, the fuel cell takes over, turning the hydrogen and oxygen gas into water as well as electricity that can then power the aircraft. So now the question becomes, how do we model the performance of this RFC? We can do it through polarization curves. They plot current density and cell potential. And something to note is that as you increase the current density, but the performance and the efficiency of the RFC start to decline. There's also three regions of note here. The first is the region where activation polarization dominates. This is caused by sluggish kinetics. The second region is this linear region where ohmic polarization dominates, and this is caused by ohmic losses in the electrodes as well as the electrolyte. And the third region is the region where concentration polarization dominates. And in this case, overpotential is caused by mass transport losses. So there's been a bit of research into using RFCs for aircraft. For example, Barbier conducted a weight efficiency trade-off for RFCs in aircraft. Additionally, Lee conducted a mass minimization of an RFC system. However, it had a couple of limitations. The first is that it only assumed a 12 kilowatt power draw, which is significantly lower than modern aircraft power requirements, which are on the order of megawatts. Secondly, it neglected parasitic losses. These are power losses incurred by systems indirectly providing propulsion and cannot be ignored in the real world. So now the rest of the presentation will focus on answering the following research questions. First, analyzing the feasibility of retrofitting RFCs into existing aircraft, and second, finding the aircraft that are the most optimal for RFC implementation. And this will be done through first modeling the RFC system mass, and then secondly, minimizing the system mass for multiple aircraft. This modeling is all an abridged version of the one that was performed by Lee et al. And requires two assumptions. The first is that there's a constant power output of the fuel cell during nighttime, and second, that there's a constant power input by the photovoltaics for the electrolyzer during the daytime. From this, we can generate this pretty complicated mathematical model. However, everything ends up becoming a constant except for three variables. First is PFC, which is the power output of the fuel cell and is dependent on the specific aircraft. Second is IEL, the electrolyzer current density. And the third is IFC, which is the fuel cell current density. The fuel cell current density and the electrolyzer current density are the two variables that will actually be changed in order to minimize the system mass. Additionally, something of note here is that the electrolyzer and fuel cell are set to operate in the region of ohmic polarization, and this allows for a linear modeling. Before the optimization can be performed, a couple assumptions must be made. The first is that there's a 90% efficiency for the electric motor. Second is there's a 5% parasitic loss. The third is that the RFC is being placed in the payload, and therefore the mass of the RFC cannot exceed the payload weight of the aircraft. Fourth is that the weight of the photovoltaics powering the aircraft during the day, plus the weight of the motor, plus the weight of the aircraft, is equal to the empty weight of a fossil fuel power aircraft. And the final assumption is that the photovoltaic can provide enough power for the aircraft and electrolyzer. And something to note is that the last two assumptions are most likely inaccurate because the power requirements are extremely high. What this means is that the weight of the photovoltaics would probably be extremely large, as well as the surface area of the photovoltaics might not even be enough to power the aircraft. We can perform this optimization using SciPy's minimize function, using the SLSQP method. SLSQP uses sequential quadratic programming, and this allows for constrained optimizations. The way it kind of works is that we have an objective function right here, and then we have our bounds, which are shown by these dashed lines. And then our solution is either the maximum or the minimum. In this example, it's the maximum, but in our case, it looks for the minimum. And in our case, the bounds are that the electrolyzer current density between 2,000 and 11,000 amps per meter squared, and the fuel cell current density is between 1,000 and 9,000 amps per meter squared. We can see how this minimum mass starts to get generated when we look at this curve. We can see a distinct system minimum right about here, which corresponds to the minimum mass of the aircraft. For using the minimum mass, we can generate a feasibility score, which is just the minimum mass divided by the payload weight. What we find is that in all cases, RFCs have not advanced far enough to be implemented in aircraft. This is because a feasibility score must be less than 1 for it to be possible to be implemented, but in all cases, it was significantly higher. And we can start to see why when we first look at it through the lens of current density. The electrolyzer current density was extremely large in all cases with very little variation. What this suggests is that there's poor electrolyzer performance. Because at large current densities, we are able to attain more power, but at the cost of lower efficiency. You can see in this polarization curve, as we increase the electrolyzer current density, it requires more potential. And this means that lots of electrolyzer cells are being used, which contributes to large mass. We can also start to see why when we look at it through the lens of the photovoltaics. In all cases, 37% of the total mass is the photovoltaics. And this makes sense when we look at the specific mass, which was very low. Coupled with the large power requirements, the mass was extremely large. And this means that photovoltaics must be made significantly lighter for these systems to become viable. We find that the best candidates are smaller one-engine aircraft, and this is a result of their lower power consumption. They don't require as much weight in terms of photovoltaics and electrolyzer cells, which makes them better candidates. So in summary, RFC implementation is not currently possible without sufficient advances in system mass reduction. Work must be done to both maximize the electrolyzer cell efficiency, which would reduce electrolyzer mass, as well as reducing the photovoltaic weight by increasing the efficiency. We also find that smaller one-engine aircraft work the best with RFCs because they're less power hungry. And something of note is that because of the lack of photovoltaics and electrolyzers, pure fuel cells may be of interest for aircraft implementation, such as providing the hydrogen at refueling stations instead. And now I just want to take the time to acknowledge everyone who made this presentation possible. First, thank you to Matthew for being a great research mentor and helping me with every challenge I faced. Second, thank you to Diego and Isaac for asking great questions and helping as needed. Third, thanks to Argonne Lab for giving me the opportunity to present my research every week. And finally, a huge thank you to SSI and its staff for teaching me all the skills I needed to conduct this research. Here are my references. Thank you for listening.